This is the Python demonstration module for the presentation number 3 on CCDs and image processing with an LSST perspective. This notebook and the associated test image are available to members of the LSST Dark Energy Science collaboration at this URL. And the objective of this demonstration is twofold. One is to demonstrate some straightforward image and header access tools using Python, and the second is to demonstrate some of the image characteristics and features of CCDs that we described in the first module. So this is a Python notebook. I kicked this off by typing Jupyter space notebook at the command line. The image foo.fits resides in the same directory as this Python script. And so we'll just go through this cell by cell and talk about how we can use Python to access FITS files. So the process starts by going through a pretty standard set of Python initialization and import steps to bring in NumPy, Matplotlib, and AstroPy and SciPy as methods that we can import. There's a command line magic command that makes Python produce the plots in line within the notebook here. And I define a couple of width and height parameters because I want to make figures that are slightly bigger than the default. So by clicking on the run module, we execute that first cell. It doesn't display anything, but now we have all that stuff imported. The Python FITS utilities demonstrate the ability to bring in a FITS file, so let's do that. This, I guess it's a method, executes and opens up a FITS file and assigns it to a data structure over here called HDU list, and we can then actually use a nice method that runs on HDU list to see what its contents are. So if we go ahead and do that, it displays to the screen a list of 20 individual objects that collectively make up this HDU list. It starts off with the primary image header, which is element number 0 in this object. There are 16 independent amplifier segments, which are these. And then actually part of this FITS image are some FITS binary tables, which are actually objects that contain the time series of photodiode calibration measurements that are used to determine how many photons were actually incident upon the image during this particular test sequence that were taken. This image that we're looking at is actually, as we'll see in a moment, a product of laboratory bench testing that was done at Brookhaven. So now that we know what the individual components are of that HD unit, we can look at the contents of the first element, which is the extension 0 FITS header, by pulling up the header that is associated with the first element of HDU list, convert to a string. This funny syntax here actually generates a readable printout on the screen because FITS headers are expecting to be put on a screen that is 80 columns wide. So this slightly obscure Python syntax actually generates a readable printout of the FITS header. So here we go. Here's the extension 0 header, and the characteristics of the data, the number of axes, the place it was taken, the time and date of image acquisition, the CCD controller, the characteristics of the CCD itself, the type of image. This could have been a dark or a bias image. This one happens to be a flat. The set point of the temperature set point of the CCD, the actual measured temperature of the CCD, the bias voltage that's applied in the vertical direction to drive the charge down to the pixels, the average of the photodiode current during the exposure, the wavelength of the monochromator, on and on. You can see there's a whole bunch of information in here that are basically metadata that describe the characteristics under which this image was obtained. That then pertains to all the subsequent extensions that are in this particular FITS file. If we want to look at the amplifier specific component for the first amplifier for extension number 1 in the FITS header, we can similarly access its header and print out what it has to show us. And so this is the entire FITS header associated with that amplifier, and it contains primarily just information that's unique to that one particular amplifier. So it tells us the number of bits per pixel, the size of the array, some checksum just to make sure that we haven't dropped a bit somewhere, the name of the extension in the LSST nomenclature, and then in particular these data section, bias section, and detector section numbers designate where within the CCD this particular amplifier resides, and information about its handedness and directionality within that Mosaic 16 amplifier object. There are some early statistics that are computed on the image, and really that's about it. So we can actually use the FITS.io tools to edit and modify and rewrite the FITS header if we so chose, but we're not going to do that. We can look down at the bottom and look at some of the characteristics of the binary table that is associated with the photodiode measurements. We would open this and access it with FITS binary table access tools if we so chose. So that's the way you can use the PyFITS utilities to access, modify, and overwrite image header metadata. If we want to reach down and grab the pixel data, just like we had an HDUlist.header component of that object, there's a .data component of the object which we can assign to an array within Python here called pixel data. So if we go ahead and do that, we can then do some simple aggregate statistics on the resulting array by reaching in and grabbing its maximum value, minimum value, and the median across the entire image. Just as a sanity check, we can verify that the array that we produced is consistent with our expectations based on the image format by interrogating the shape of that particular array within Python, and sure enough we get 2048 rows by 544 columns, which was in fact what we expected by looking at the FITS header that we interrogated earlier. We can peek at individual pixel values within the array. The very first pixel to be digitized is stored as element 00 in this amplifier pixel array. We can look at the first pixel, we can look at the first imaging pixel, we can look at the pixel near the center of the array, we can look at the last pixel in the array, just by accessing appropriate integer index-based values that reside within the pixel array. And you just have to remember that the first index in the Python array is the row in the image, and the second index is its column. And we can access a slice of the image by just giving a range with the colon operator within Python and spit out a range of 4 successive pixels. And just to remind people who are coming to Python from other languages, in these slices, you don't get the 205th value. You get 201, 202, 203, and 204, which is 4 pixel elements, and here they are. Those are the integer ADU values that reside within those 4 pixels. We can use the display tools within Python to actually show an image as a grayscale of that particular 2-dimensional pixel array that we read in. So if we go ahead and do that, sure enough, we'll get a display of the amplifier image with a grayscale representation of intensity. A color bar on the right-hand side is invoked by this method running in the Matplotlib toolkit. So sure enough, we have something that looks like sort of what we expected. If you recall, we should have pre-scanned pixels, overscanned pixels around the edge, and this is shown on the screen with element 00 being in the top left corner. And at least for me, I'm a lot more accustomed to thinking about these things flipped around the other way, with the first pixel read out being in the bottom left corner. It's easy enough to invoke the imshow utility and change where the origin is and flip it around so that it's actually more conventional from my perspective. So this is the way I'm accustomed to looking at amplifier images, where now the bottom left-hand corner contains the amplifier, the serial register runs in the horizontal direction, and the pixel flow is from the top, marching down with parallel transfers, and then out to the left with individual shifts in the serial register. And now we can see that the pre-scan is fewer pixels than we have in the overscan, and this is the overscan row region up here at the top above row number 2002, where phantom pixels are read out and stored in the array. So with that sort of mindset, we can then start doing some fun stuff. One thing you might want to do is to make a histogram of the pixel values that are in the array, and you might want to do that with some outlier exclusion by doing 3 sigma clipping. So here's a scrap of code, and thanks to Jim Chang at Slack for helping me with this. The method that produces histograms is expecting a one-dimensional array of numbers and not a two-dimensional array of numbers. And so this entity, pixeldata.flat, actually takes the two-dimensional array and puts it all in a one-dimensional array of numbers. There's a method within AstroPy statistics module that does sigma clipping at the 3 sigma level, and so we've produced an array here that's a one-dimensional array that's the subset that satisfies the condition that the values not exceed 3 sigma relative to the mean. We can plot that in a figure over an appropriate range as a histogram and give it a name, and we can go ahead and do that. And the histogram that results is quite sensible. So we have, typical values of around 20,000 ADUs. It looks relatively Gaussian. It's clipped here because of the 3 sigma clipping that was imposed, but by and large, this looks pretty healthy. We can also come in and just actually, within the subset of the array that contains the imaging pixels, compute the standard deviation of that object, and then take the ratio of that standard deviation to the mean in the same region, and that's the fractional variation of values without doing any sigma clipping here, and compute the sort of width of this histogram effectively normalized to its mean value, and we see that that's around 1%, and the LSST spec is around 5%, so nominally this imager looks pretty good. In the assumption that we've done uniform illumination, it seems to deliver pretty uniform pixel values. So that all looks good. Having done some interrogation of individual pixel statistics and making Gaussians, we can now make one-dimensional plots, essentially cuts across the image, to start visualizing the uniformity of the response and any spatial structure that it may have. So the first of these is going to be a row plot, which is essentially a horizontal cut across this image. We're going to take a given row and make a plot of pixel values as a function of column number. We can also go in the other direction and make a vertical cut down the image and plot pixel intensity value as a function of row number, both within the imaging region and within the overscan region. So let's go ahead and do that. I've tried to be consistent where if we make plots that are running horizontally across the image versus column, they're blue graphs, and going in the other direction, red, to try to develop some intuition about the two different cross-cutting directions across the array. So the first of these, since it's 530 odd columns across, is the horizontal cut across the image. So we're plotting intensity as a function of column. This is the pre-scan pixel in the row. Here are the pixel values in the imaging region, and then it drops down to the overscan for that particular row. Going the other direction, on the left-hand side are the rows that are down at the bottom of the imager. Move up to the imaging part of the array. There's some funny excursion here, and then it drops down to the value of the row overscan at the top of the image. That's within the imaging region of the detector. If we move over further to the right-hand side and plot the values in the overscan region alone, a vertical cut across the array looks something like this. The pixel values are pretty uniform. But there's some interesting stuff going on here. So for one thing, at low row numbers, you can just see here that the flux is diminishing. And so let's zoom in on that region and see if we can figure out what's going on. So we're just going to plot a subset now over a limited range of rows, the first 30 rows, picking column number 200, and let's see what that graph looks like. So as you come downward to diminishing row number, the pixel intensity values start to drop by a pretty substantial margin. And that seems indicative of something that we should investigate a little further, but things are kind of bouncing and rattling around. So maybe a good thing to do might be to average over multiple columns, and that's an easy enough thing to do. I can generate an object called average column by taking a mean where I collapse 100 columns together, take their mean from top to bottom over the entire image, and this axis value tells the NumPy mean operation which direction it's my intention to average this subarray over. So we can then plot that using slightly better statistics and look at the bottom at low row values. We can also make a zoom in plot up near the top because there's something funny happening up here at the top end as well. So we'll plot that averaged column and zoom in on low and high row numbers respectively. So the top one of these is up at the top of the image, up near the midline, which is the separation point where charge below that midline flows downwards to serial registers at the bottom of the CCD, and above the midline flows upwards to serial registers at the top of the CCD. This particular detector has that midline implant, and you can see that the last row at the top of the array has a diminished value relative to the mean, but the one right next to it and moving further in have augmented flux values. There's also some anomaly over here about 11 rows below the midpoint of the imager. And this is all phenomenology that we now understand. That midline barrier within the array actually produces a repulsive lateral electric field that pushes the charge away from the midline down towards the serial register. So this pixel's effective size is diminished, and the ones next to it have sizes that are essentially augmented relative to the mean, and that anomaly persists for 1, 2, 3, 4, 5, 6, 7, 8, 9, maybe 10 pixels into the array before it stabilizes. This we understand, this excursion of diminished flux about 15 rows or so below the midline, we understand comes about because of a mask anomaly that is intrinsic to every single one of the amplifiers in these chips. This can be flat fielded out and is not actually a substantial problem to us. So this is the first example of us encountering something that we can now explore quantitatively that we describe qualitatively as one of the features that afflict LSST CCDs. Looking now at the bottom of this amplifier segment close to the serial register, the first few rows that are read out have diminished flux relative to the median in the array, and we understand that coming about because of that edge roll-off syndrome. So down near the serial register, the charge can feel the electric field from the scupper that surrounds the CCD imaging array, and that produces this suppression of flux, which essentially you can think about as a variation of effective pixel size under uniform illumination. So that's something that we understand, but it's nice to see it emerge as a quantitative plot. Let's look at the spatial structure of the chip sensitivity in the column direction, looking only at the imaging pixels, and see what we can learn about the structure of that sort of 1% variation in sensitivity that we saw. So we can go ahead and run this little scrap of code here, and this is now a plot of an average of essentially, this is a plot of that average column across all rows in the image. And we've normalized it now so that the mean is sitting here at 1. And you can see there's this big excursion at low row numbers that we understand to be edge roll-off. There's this big excursion at high row numbers that we understand are rising from that midline bleed stop. So why don't we just zoom in on the region of the imaging array that omits those two now understood features. And if we zoom in to the subset of rows that exclude those big anomalies, this is the plot that results. So what do we see here? There's some low order modulation over large length scales that appears to have some periodicity to it, and superimposed on that is either noise or structure at higher spatial frequencies. So if we think about it that way, it might be amusing to do a spatial Fourier transform of this one-dimensional average column and just see what we can see about the periodicity of the structure. And in particular, I'm interested to know whether these high-frequency components are periodic or just random noise. So it's a pretty straightforward thing in Python to do image processing and implement a spatial Fourier transform. So let's do the following thing. Let's go ahead and create an average column 2, which is just the subset that includes the interesting region, and we'll clip it in the row direction by omitting the rows on the bottom and omitting the rows on the top. We'll take a chunk that's about 400 columns wide and average them all together and generate this new average column over the region of interest within the segment. Next thing to do, since we want to look at high frequency structure, is to do a high pass filter operation on the image. An easy way to do that is to first do a low pass filtered version by taking a median over 51 by 51 pixel region. So this takes a 51 by 51 pixel box and rasters it around the image and replaces every pixel centered on that box with the median of that surrounding region on the array. And then the high pass version of the image is the original version, subtracting off that low pass component, the low Fourier components. So average column underscore HF is the high frequency content of the image. Since we're about to take a Fourier transform, it's my sort of rigorous best practice to always subtract off the mean before taking a Fourier transform. So this accomplishes that task. This is now an object. This high frequency average column is now an object that has a mean value of 0. And then reaching into the Python toolkit and grabbing a spatial Fourier transform, this block of code computes a spatial FFT on that object and does appropriate normalization to give a logarithmic representation of spatial power as a function of frequency. And we can then just go ahead and take a look and see what the plot and the Fourier transform look like. So this graph is the power spectrum of the high frequency structure in the averaged column as a function of spatial frequency. The highest spatial frequency that we interrogate is the frequency that is just barely Nyquist sampled, and that's 2 cycles per pixel. So this is 2 cycles per pixel. Down here at 0.05 would be 20 cycles per pixel. So this is essentially, other way around. This is 2 pixels per cycle. And so down here is 10 pixels per cycle of spatial frequency. So there's clearly a high significance, because this is logarithmic in the y direction, a high significance periodic spatial structure in the array with a fundamental frequency of around 10 cycles per pixel, of which this is the second harmonic, I think. Now it's not exactly lined up with 0.2 cycles per pixel here, which would be, I always have to stop and think about this. This is lower frequency. So this is 10 pixels per cycle. This is 5 pixels per cycle. It's not exactly lined up, the second harmonic, on 5 pixels per cycle. So I don't think it's quite exactly a mask step repeat issue. I think it more likely comes about from laser annealing on the backside of the device. And we'll talk about that as we move forward here. But clearly there's statistically significant spatial structure in the array. If we then ask, well, okay, if that's true, can you actually see it by eye? So here's a zoom in over 100 rows of that average high frequency column structure. And sure enough, you can see this periodic structure in here that's sitting here at about 10 rows per cycle. So it is quite apparent by eye in the data. That's not a random sequence of data points. Turning our attention now to the overscan region, it's a good idea to always plot the overscan structure in the array just to see if there's any evidence for temporal or spatial variation within the overscan. So this computes a average overscan column, which we then plot. And just for giggles, I then took that object and did a second order polynomial fit and overplot that second order polynomial just to see if there's any significant low order variation over the course of the overscan during the time over which the image is read out. So here's a plot as a function of row number of the pixel values in that average overscan column. And overplotted in this next plot is the second order quadratic that was the fit to that data set. And if I ask myself, what's the sort of maximum to minimum value span within the overscan, it's about a third of an ADD converter unit. So the bottom line here is that the overscan here is essentially structureless in the vertical direction, and I could just as well represent it as a single number and subtract it from the array without introducing errors in the offset subtraction. What about going in the other direction? What's the structure of the overscan as a function of column number? So now we're looking along a row, and here we see some really significant stuff going on. So down here is the asymptotic value in the overscan region, and as you start moving into the imaging array, there's again evidence of this edge roll-off problem. This particular amplifier that we read in, if you recall, was amplifier segment 1 within the HDU structure. That's an amplifier that sits on the edge of the CCD. So the serial register is always adjacent to this scupper, and the rows at the bottom of the amplifier segment always exhibit this row response. The 4 amplifiers that have a vertical side that's adjacent to the scupper exhibit this edge roll-off along the edge that's at the edge of the CCD. And so this is just another manifestation of that edge roll-off problem. So if we don't want to get led astray by that, it'd be a good idea to look at an amplifier that resides closer to the center of the CCD. So having seen this edge roll-off problem, let's just go make another pixel data array by grabbing a different extension in the FITS file and see what their overscan properties look like. So here's the end of the row dropping down to the overscan precipitously for this image segment number 5 as compared to the one that resides at the edge of the array where the pixel size is effectively distorted because of the lateral electric fields at the edge of the CCD array. So we can now use this transition from the imaging array into the overscan to quantitatively measure the charge transfer efficiency of this particular amplifier. So from looking at this image, it's clear that by the time we get out to sort of pixel number 523 and onward out to 544, that all looks like a pretty flat region of the CCD. So I can go into that part of the array and pull out for that subset of columns for all rows, ask what's the standard deviation of the pixel values in there, and use that as an estimate of the read noise for this particular amplifier in ADD converter units. And so printing that out to the screen, I see that the read noise is about 2.6 ADD converter units. That sounds pretty good. If you ask, just for giggles, what happens if we start including more and more and more columns moving to the left here, if we include the very first overscan column, the read noise goes up to 3.21 ADUs. That's because there's a little bit of excess charge sitting over here in this guy, and he's not quite at the asymptotic value of the others. And if we make the mistake of including this last imaging column, then the read noise skyrockets, not surprisingly, and the standard deviation goes through the roof. Man, that's just to demonstrate that we're doing something sensible. We can use the ratio of the bias subtracted value of the first overscan column relative to the bias subtracted value of the last imaging column in order to estimate what the charge transfer efficiency is in this particular detector. So I just go in here and determine a offset by taking the mean of the value of this little trimmed overscan subarray and take this ratio, subtract 1, and that's my seat of the pants estimate for the charge transfer efficiency just taking the ratio of pixels, and it's 1, 2, 3, 3 nines 5 basically. That's a little bit less than we'd like. We're really looking for charge transfer efficiency that's better than that. So let's try to be a little bit more sophisticated. If every single charge transfer leaves behind some fraction 1 minus charge transfer efficiency of the original value, then starting with n equals 0 as the last imaging pixel, the column dependence of the flux value in the overscan ought to obey this relationship, because the first overscan pixel contains the charge that was left behind from the original fully populated image pixel, and the one after that is the charge that didn't transfer, and so on. It's a recursive relationship. So if I take the log base 10 of that entity and then do a fit, the slope of that should basically tell me what this charge transfer inefficiency is. And I can go ahead and take the logarithm. I take an absolute value in here just to be sure that we aren't taking logs of negative numbers. And here's the log of the flux as we move from the last imaging pixel into the overscan, and it's got this kind of exponential structure to it. If I just look at the first 3 of these, if the model for charge transfer inefficiency here were correct, I would expect all 3 of those to define a nice straight line. The fact that they don't gives me pause and makes me think that there must be something going on here other than simple charge transfer inefficiency. Maybe there's a trap in the serial register that has some time constant and the charge comes bubbling out of that. That certainly requires further investigation. But let's move forward and do by hand one of the first image processing tasks that happens in a typical image processing pipeline. So here's what we're going to do. We're going to compute a single number as the bias value from looking at a region of the overscan that spans all rows in the array, but for a subset of columns that are out here where the overscan has stabilized. So we're going to take the mean in that region of the image and declare that to be the bias value that I'm going to subtract then from the imaging array. So having subtracted that off, I get a new object, and I'm going to call it pixel data 5, because it came from segment number 5, underscore bias, meaning I have subtracted the bias so that the name tells me how far it's made it down the image processing chain. Having done that, I'm going to make a bias subtracted trimmed 2-dimensional representation of this data that clips the image to include only the portions of the image that are actually within the imaging array, so I'm throwing away all the overscan. And then I just thought I'd try something a little bit fun here, and that is to auto-scale the representation of this image when I put it up on the display. So the way I did that was to make a 1-dimensional array of all the numbers that inhabit this imaging section, sort by ascending value, and call that sorted pixels, because then it's a fairly easy thing for me to go in there and ask, what's the smallest pixel value, what's the highest pixel value? But importantly, just by going 5% down this sorted array, I can pull out the pixel value that is at the 5% extreme of the intensity distribution, and by finding an integer index that's 95% of the way down the 1-dimensional sorted pixel value array, I can find the intensity below which 95% of the pixels reside, and then I can invoke this image show command by basically doing the grayscale stretch between the 5% and 95% values, and just for fun, instead of having a grayscale representation of intensity values, we'll do a color representation of intensity values, and we'll do it with the amplifier in the serial register at the lower left corner of the image. So let's see what we see. So that's a nice representation that actually shows, even visually, the different features in the image that we saw when we made column plots of the array. So the fact that this bottom edge has diminished flux values is the edge roll-off down at the serial register. This dark line across the top of the image is that one dark row that we attribute to some mask defect up at the top. And you can see there's this sort of high flux structure up at the top that's the resonance off of that midline bleed stop. This banding structure across the array at low frequencies is essentially, scrolling way back up to the plot that we had, is this modulation. And you can even just barely see, if you look really carefully, I think, the high frequency structure at the 10 pixels per cycle superimposed on top of that. So we've gone through an exercise where we started by cracking open a FITS file, looked at the header information, assigned the pixel values to a two-dimensional array within Python, did some one-dimensional line and column average plots, extracted summary statistics from the overscan region, and then went through by hand one of the initial stages of image processing pipeline flow, which is to determine an overscan, to determine a bias level from the overscan, subtract it from the image, and trim the image so that we're left over with just the imaging portion of the array. Whether or not we would find it advantageous to trim off these edge overscan contaminated pixels at the bottom depends upon the fidelity of downstream operations and how well we can in fact correct for that. So that concludes this particular demonstration of Python interrogation of LSST FITS images.